time, our ancestors went beyond mere survival, and they looked around them when they had a moment of relaxation, and they wondered about the world around them. They asked questions such as, how has the world started? What is the world made of? Then they related that to themselves and asked, what am I made of? What am I? In this talk, I'm going to talk about this question, what am I made of? And about a discovery that was made by physics 2 years ago, the Higgs Boson. You might have heard about it in the media. It made a lot of buzz 2 years ago, and the Nobel Prize was awarded. And I was one of the many people working on this project. But before I can tell you more about this discovery and its implications, I want to tell you how different sciences answer the same question of what am I made of, and how this relates different sciences with each other. To do that, we look at sciences as a pyramid, the same way we look at an ecosystem as a pyramid, with few predators at the top, many at the bottom, each layer feeding on the previous layer, which is more populous. And if you do like that, what do you think is at the top of the science pyramid? Well, it's psychology. Psychology says, I'm consciousness. That's how it answers the question. And there are about 7 billion consciousness in the universe, as far as we know. But we know that each organism is made of hundreds of billions of biological cells. So I could say that psychology is actually applied biology. And biology answers, I am cells. And of course, cells are made of molecules, so biology is applied chemistry, and molecules are made of atoms, so chemistry is actually applied physics. Now, physics is so cool that it has different subdomains, because atoms are made of smaller things, that are made of smaller things, that are made of smaller things. And therefore, we can dedicate an entire slide to that. Indeed, atomic physics says we are made of nuclei and electrons. Nuclear physics says the nucleus is made of protons and neutrons. Particle physics says protons and neutrons are made of even smaller things called quarks. So these quarks, along with the electron, form the elementary particles, the elementary ingredients of the universe. So particle physics says I am 3 particles. All the diversity in the universe is explained by these 3 particles. And historically, they are the first one that appeared at the creation of the universe. Our ancestors asked, how has the world appeared and what is it made of? Well, this is what it's made of, and it appeared, of course, in the Big Bang. Before the beginning of the universe, there was only energy and the laws of physics. So what happened is that energy transformed into particles. We know from Einstein, energy is equivalent to mass. That's what meant. Energy became the mass of new particles. And of course, these particles produced atoms. And from atoms, everything emerged. Molecules, and then biological cells. And we can exist because atoms can exist. But we can exist because atoms not only exist, but they live for a very long time. They are stable. Without this, they wouldn't be able to have cells and molecules. You know that expression, nothing is destroyed, everything transforms. It refers to the atoms. Once produced in the stars, they are never destroyed. And everything transforms. It means atoms are shuffled around between molecules and biological cells, and that's what gives us all the diversity in the universe. So I could argue that a bigger wonder than the origin of life is the origin of atoms, and why they are stable, why do they live for a very, very long time. And indeed, we created a theory that explains that, how we go from elementary particles to atoms, and that is particle physics. And as you see, it's the science that is at the foundation of the pyramid of sciences. It's the most fundamental science we have because it talks about the ingredients that are fundamental to our matter. It's the things that appeared shortly after the Big Bang and from which everything else was produced. By interactions, we mean forces. For example, the electric force keeping the electron and the nucleus together to form the atoms. So the particles and their interactions, that's what we study. And this theory works perfectly, and it's confirmed by all experiments completely. But something was missing, and that was the origin of mass. Mass of the elementary particles is important because, as we know from Einstein, mass determines what is the speed of the particles can acquire. And there are only 2 possible cases. Either mass of exactly 0 kilograms or larger than 0 kilograms. 0 kilograms means always traveling at the speed of light, which is very fast. The largest speed in the universe. So the particle of light, the photon, travels at the speed of light. On the contrary, particles we are made of, such as the electron, They have a tiny mass, but still strictly larger than zero, which means they can never reach the speed of light, which means they can be at rest, zero speed, or can move slowly. And as you'll see, it is the ability to move slowly that allows electrons to stay in atoms. Because imagine if an electron had zero mass. It would go with the speed of light, it would jump out of the orbit of the nucleus you see there, so the nucleus would remain alone. Atoms wouldn't exist, so we wouldn't exist. But because the electron has a mass, the electron can move slowly, and therefore be stable around the nucleus and create atoms, which allows us to exist. So I showed you that because electrons have mass, we exist, and we didn't know why this was the case, and without it, we wouldn't exist, so it's a fundamental question of understanding of our origin. To answer this question, 50 years ago, these two gentlemen, along with 5 others, had a truly revolutionary idea. One of them is local, Peter Higgs at the University of Edinburgh, and he's the one that lent the name to the whole discovery, but of course everyone here contributed. Before I can tell you what their revolutionary idea was, let me introduce an analogy. You have here a forest made of trees, the green dots there, and you have 2 people, a small person in red, a large person in blue, and they ask to run through the forest, and the trees are very, very close to each other. So I ask you, who do you think will arrive first at the other side of the forest?
The large guy.
It is the small person. Why? Because the small person can squeeze easier through these trees. In other words, the person will see fewer collisions with the trees. Or if you think of the forest, it will see a smaller friction from the forest, so therefore can go faster. On the contrary, the larger person will collide with more trees, will see a larger friction from the forest, and therefore be slowed down because he has a larger mass. The same way they thought. Everywhere in the universe, absolutely everywhere, there is something we call the Higgs field, and this Higgs field is represented by the forest. The Higgs field is made of Higgs particles, or Higgs bosons, represented by the trees. And as particles move through space, they will collide with these Higgs bosons, be slowed down by the Higgs field, and therefore, once you go down from the speed of light, as you just saw before, it means you cannot have a mass of 0. You have acquired mass. And they say that the larger the mass, the larger the interaction with the Higgs field, and that's how you can acquire mass. And this field, they say, is everywhere. In me, in you, but even in empty space, when there is nothing in the cosmic space, there is a Higgs field. That's why they say, that's why it's a revolutionary idea. They say the space is not empty anymore, it's filled with this Higgs field. But is it really true? To know if it's true or not, you have to go to the experiment. Because in science, it is the experiment that is the supreme judge of a theory. You have to test all their theories, all their predictions, and this theory has only one prediction. And that is the existence of a new elementary particle, the Higgs boson. In other words, in order to believe the forest exists, you have to see one tree. Moreover, you have to see the tree in 2 experiments at the same time, independently, because maybe there was a default with the experiment in one of them. And that's what happened. CERN, the big particle physics laboratory in Europe, basically collected 10,000 people from around the world, it's an international collaboration in fact, for the last 20 years, and designed and built these 2 experiments. And 2 years ago, independent of each other, they both found the Higgs boson. So now we confirm that that tree, that field of Higgs bosons exists, and we understand why particles had mass. And here's where I come into play, because I was one of those 10,000 people that were judging their theory. So I'm an experimental particle physicist. Already when I was in high school, I learned about Higgs boson and CERN, and I dreamt to be part of the generation who finally answers this question, yes or no, the Higgs boson exists. This has been the Saint Grail of particle physics for the last 30 years or more. So I was hooked. And as soon as I had the opportunity, in my 3rd year of undergraduate in France, I joined the Atlas experiment and dedicated my thesis to that experiment. The CERN experiments got delayed in their construction, so I moved to Canada at McGill University, where I joined the American laboratory Fermilab at their experiment CDF. They were leading the world in searching for the Higgs boson for the previous 25 years before CERN. So I spent there my master and my PhD looking for the Higgs boson. And 3 years ago, I joined Glasgow as a postdoc, and I continued coming back to the Atlas experiment to do the same thing. And indeed, the Higgs boson was discovered. So in the next few slides, I want to tell you how we did to discover the Higgs boson, and in the meantime, give you a glimpse of what it means the life of an experimental particle physicist, such as myself. First, we need to create these particles. We need to zoom in inside matter, so we need a microscope. And our microscopes are as big as a city. That's the city of Geneva, the Mont Blanc mountains in the background, the Lake Léman, and 100 meters underground, 27 kilometers in circumference, you have the Large Hadron Collider. This is the machine. And you can see the tunnel that we have there. And this is the thing that rarely produces a Higgs boson. It is ironic that to see the smallest components of the universe, which are points that appeared right after the Big Bang, you have to have a huge machine of a huge microscope. So why is that? Remember how particles were produced right after the Big Bang? Energy became particles. Einstein says energy is equivalent to mass. We do the same thing. Where do we get the energy from? From the energy of movement of protons. Movement means velocity. That's why we accelerate them. That's why it's called an accelerator. And in fact, we accelerate them to speeds so close to the speed of light that only 12 meters per second means to the speed of light of 300,000. That's how close we get to the speed of light, and that's what allows us to transform the energy of movement into new particles. The Higgs boson has a mass of 130 times the mass of a proton. It wasn't in the proton in the first place, but by colliding protons, we produce new things that were not there, just as we did in the Big Bang. Now, the Higgs boson decays right away, so we can only hope to see it with these daughter particles. To see that, you need to take a photo, so we need a digital camera, and for us, we have particle detectors. They are as huge as this building. See how small the person is on that scale. Two beams come horizontally, they meet in the middle of the detector with that speed close to the speed of light. Higgs boson produced, decays, daughter particles go vertically and transverse the different layers of the detector that you see with different colors. And that is because different layers interact differently with different particles. That's allowed us to see all sorts of different daughter particles. So we do police work to find out what are the daughter particles, and then we do detective work to find out what is the mother particle. Was it a Higgs boson? Because the detector is digital, a digital camera, we store the information on a computer, 0 and 1, and this is why we use computers to analyze this data. In fact, we use supercomputers, and that's a real image from CERN, because the vast amount, the data is so vast. So what do I do in practice in our everyday job? I program. Physicists had to learn to program to become software developers to analyze this vast amount of data. And indeed, we found the Higgs boson. And here's an example of a real data, a Higgs boson candidate, where a Higgs boson produced in the middle decays to 4 electrons. The daughter particles are electrons, the particles we just discussed. As you see, the environment is quite busy, and that's why it took so long for it to be found. But we did it, Atlas and CMS, and because of that, the two scientists were able to receive the Nobel Prize. Two theorists received the Nobel Prize 2 years ago, but that was thanks to the work of 10,000 people for the last 20 years from around the world. It was the first time in the history of science that you needed such a large effort in order to prove a theory. So the Nobel Committee felt obliged to mention the experiments explicitly in the background. Atlas experiment, 3,000 people. CMS, 3,000 people. That's as big as a large company. The accelerator people, another few thousand people. So I felt privileged to be part of that 10,000 people and to fulfill my high school dream of being part of this generation to answer this question. And on a more personal note, I was also privileged to have met Peter Higgs himself and presented the results from our research. This was from the American laboratory just 1 month before the CERN discovery, and at that time it was the closest hints we got to seeing a Higgs boson, so he was happy to learn about that. So now that we found the Higgs boson, a chapter has closed. So what have we learned? We learned that in order for us to exist, we need atoms to live for a long time. In order for atoms to live for a long time, we need for elementary particles such as electrons to have mass. To have mass, they have to go slower than the speed of light, and that was achieved. We didn't know why, and the theorists predicted, and we explained experimentally that this is the case, that everywhere in the universe, in space, there is this Higgs field. As particles move through space, they are slowed down. Slowed down means mass, and slowing down, they can stay inside the atoms and we can exist. So a chapter has closed, and another one is opened, because now we can study the Higgs boson in more detail, and that can tell us even more about the nature of even space itself. What is the big discovery? What is the Rubicon it crossed? We can never go back to a time when we said we thought space was empty. Even empty space in the cosmic space is filled with this Higgs field. And they are together. Space and Higgs field go together. So by studying the Higgs boson in laboratory, we can learn fundamental things about space. Space tells matter what must to acquire. Is it possible to do the opposite in the future? Manipulate space in some way? We can only dream. But to give you an example of science fiction, so it's just science fiction, but something that makes us dream. You all know Star Trek. They travel to distant stars. But they loved Einstein. They said, we don't want to contradict Einstein. We don't want to travel faster than light. What do we do instead? We manipulate space around the ship. We bend to the space and we send it backwards, and then the ship advances forwards, but every time I go slower than the speed of light. So who knows if we can manipulate space in such a way? But we can only dream, and led by curiosity, just as our ancestors, we looked at the world around us and asked what we are made of. And that journey took us to the beginning of the universe, to the elementary particles that constitute us, and then to the nature of space itself. As CERN continues to collect new data at higher energies and intensities in a few months, we will do more research, and who knows what great discoveries will come, because our quest for knowledge continues. Thank you.